In this video, we're going to look at experiment 17 and the titration of a polyprotic acid experiment. So some of you guys did the titration of a monoprotic acid already, so you may have a little bit of a better sense of how this experiment's set up, how the experiment's set up, and what you actually do in lab. For those that haven't, we're going to try to simulate this in this video as best as possible, so you can actually see where everything goes and what we're putting together. So in this experiment, what you would do in lab is we're basically taking a polyprotic acid. Polyprotic just means that it has more than one acidic proton. So like phosphoric acid has 3 acidic protons. And then we're going to neutralize it with a base, a strong base, like sodium hydroxide, until all of those acidic protons are reacted. So we're going to make sodium phosphate in the end. Now, there are a couple of questions that I like to start this lab with, and I kind of give away already what you're going to see in the experiment right away. So this is what the titration curve is going to look like. It looks kind of like what we got with a monoprotic acid, but there's a couple of different things going on here, and we have to start to dissect this. So let's start thinking about this. So how many equivalents of hydroxide are required to titrate H3PO4? So the reason why I want to start you guys thinking about it this way is because if there are 3 protons, in the end of the experiment, we have to use 3 moles of base. So as you can see here, the stoichiometry is 1 to 3. But what's interesting is when you look at the shape of this graph, there's not one squiggle where we get to the equivalence point after adding 3 moles of the NaOH. There are 2 squiggles that we can see here. So something is going on. This tells us that the process is not taking place all at once. Something is reacting, and then there's another thing that's reacting, and the reaction is kind of taking place in a sequence. Because if you basically look at this, this kind of looks like the titration curve for a monoprotic acid. And then this also looks like the titration curve for a monoprotic acid. So, and they're kind of overlaid on top of each other. Now, if we dissect this graph even a little bit more, you'll notice that as we add sodium hydroxide, the pH goes up, so that makes sense. We're adding base, so the pH goes up, but it kind of stays relatively flat for a while, and then it goes up rather rapidly, and then it kind of stays flat for a while, and then it goes up rather rapidly. So the shape here suggests that we may have 2 buffers, where we have 2 sort of flat regions, and we may have 2 equivalence points that we can see already. So there are some complexities to this graph that we have to address, and that's what we're going to kind of start with from the concept of polyprotic acid titration. So if we look, there are 3 possible steps that we could have in a polyprotic acid titration, right? So we can take H3PO4, which is the fully protonated acid. That's the phosphoric acid. If we do our first equivalent of OH-, we can get H2PO4. We basically take one of the protons off, we turn that into water, and then we're left with a singly deprotonated acid, H2PO4-. Then if we take that and we put it into the reaction again and we add a second equivalent of base, we get the monoprotic HPO42- and water. So we take off the second proton, then this guy can go and react again, and we can get the third proton off, giving us the final product of PO43-. So if you add all 3 of these reactions up, what you wind up getting is the original reaction that I had written before. It takes 3 equivalents of base to fully react PO43-. Now the data suggests that we're doing something like this. We're seeing this happen in steps. So the question is why does titrating a polyprotic acid result in a sequential titration? So why don't all of these protons just kind of come off all at once? And the answer lies in the fact that really what we have is 3 acids built into one. So because we can generate these 3 different species, we can write Ka equations for each one. So if you look, I do that for H3PO4, and this is the classic Ka equation. We take the acid, we react it with water, we make the conjugate base, and H3O+. And then we can write a Ka equation for that species, where the 2 things in the Ka are the H2PO4-, and that's the conjugate base, and the acid H3PO4. And then we can do the same thing for H2PO4- and HPO42-. So each one of these can have its own Ka equation, meaning it can deprotonate and make an H3O+, And we can write those Ka. So we have Ka1 for the first proton, Ka2 for the second proton, and Ka3 for the third proton. Now, if you go back to your notes in chapter 15, what you're going to remember is that as you take protons off, the trend for acid strength is that the acid with 3 protons is going to be stronger than the acid with 2 protons, which is going to be stronger than the acid with 1 proton. So in essence, Ka1 has got to be greater than Ka2, which has got to be greater than Ka3. So if you think about that, what's happening is when you add base, so as you start to put the OH minus in, that OH minus is going to attack the strongest acid first. So the strongest acid that's around is the triprotic H3PO4. So even though we're making H2PO4 minus as we add base, when we add that base in, it's going to go and find that strongest acid and react with that first. Once that's all gone, once the H3PO4 is all gone, then the only thing that's left is the next strongest acid, H2PO4 minus. So then it starts reacting with that one, and then finally, when that one's all used up, it reacts with the HPO42 minus. So the reason why we get this sequence is because of the decreasing acid strength as we go to fewer and fewer protons on the acid. So now let's sort of navigate the titration curve. So what's happening in this titration curve? So we're going to kind of start from the beginning. We're going to take our acid, we're going to put it in a beaker, and we're going to start adding base to it. So we have our acid in a beaker and we start adding base. So what you notice is that we have the behavior of what looks like a weak monoprotic acid, right? We see a buffer region, and then we see the pH start to rapidly rise, which is suggesting that we're coming to an equivalence point. And right in the middle of that rise is going to be the first equivalence point. So as we add the base for the first proton, we're going to start to make a bit of H2PO4 minus, and we're going to have some H3PO4, that's the triprotic acid in there, and the diprotic acid in there. So in the very beginning of this experiment, we're going to have a mix of H3PO4 and H2PO4 minus as we add the base. So this is going to give us our first buffer, where we have the triprotic acid and the diprotic acid as the conjugate base. Then, once we've added enough OH minus to fully react with the H3PO4, what we're going to have in solution at the first equivalent point is just H2PO4 minus. We've used up all the H3PO4, we've turned it all into H2PO4 minus. So at the first equivalence point, we get 100% H2PO4 minus. And then basically everything starts again. So since we only have H2PO4 minus left in the solution, as we add more OH minus, we make the HPO42 minus conjugate base. This is the monoprotic form of phosphoric acid. So again, what we're going to see is we're going to see a buffer region. As we start to titrate this, we're going to make a little bit of the conjugate base. So in buffer region 2, we're going to have H2PO4 minus and HPO42 minus together. So that's going to form a buffer and form a little bit of a flat line. And then what happens is, as we get close to using, once we use up all the H2PO4 minus and make HPO42 minus, we get our second equivalence point. So at this point, all of this is used up, and now we have all HPO42 minus in there. And then we can do the same thing. We can start to take off the third proton, making the fully deprotonated conjugate base PO43 minus. So again, we're going to get a buffer region with a mix of the HPO42 minus and the PO43 minus. So here we're going to have a mix of these two until we get to the third equivalence point, where then we've reacted all of our acid, everything is gone, the only thing we have left, we've reacted all 3 protons, so that means that the only thing we have left is PO43 minus. Now what's interesting is you can see here, these 2 equivalence points look beautiful. They're nice and clear and sharp. But then for the third one, you look at this and you go, I don't see an equivalence point. There's no sharp rise. The buffer region doesn't even look like a buffer region. So the question is why does this thing start to get washed out when we get to the third equivalence point? So the reason for this is we have to kind of think about this in terms of where is that Ka3. So if you look it up in the book, the Ka3 for phosphoric acid, the Ka3 is 4.2 times 10 to the minus 13. this is a very, very small number. Actually, it's so small that we're starting to approach the value for Kw. Now, if you remember back in chapter 15, the requirement for an acid, for something to be an acid, it has to have a Ka that's greater than Kw, right? So its Ka has to be greater than Kw in order for it to be an acid. So in this case, we're getting to the point where we're just barely an acid anymore. So we're barely getting past, meaning that water is just about the same acid strength as the HPO4 2-. So that means that the concentration of H3O plus and OH minus in water are going to start to wash out the concentration of the H3O plus that comes from the Ka3, and we don't see it anymore. The other reason is, as we're going along and adding volume, so this whole time we're putting in base, and that's increasing the volume of our solution, we're just diluting everything at this point. So as we add volume of base, the concentration of the acid gets diluted. So not only is this a weak acid, a very, very weak acid, very, very close to the strength of water, it's also getting more and more dilute as we go along. So it essentially becomes impossible to see because the OH minus concentration from water just washes it out. Okay, so how do you set up this experiment? So if you were to be in lab, what you would do is you would take a beaker and you'd put it down, and what we would do is we would take 25 mils of the unknown polyprotic acid solution. So we would use a volumetric pipette to transfer 25 mils of the unknown into our beaker, and then in our burette, which we would clean and put standardized NaOH in, we would set that up, and then we would have the burette going into the beaker to add our base. So in this experiment, the base concentration that you're going to use is 0.1012 molar. So the virtual students that did this experiment last year, the data that we're sending you was done last year by students. Their concentration of base was 0.1012 molar NaOH. And they used exactly 25.00 mils of the unknown polyprotic acid solution. So once you have that set up, you stick your pH electrode in, which measures the pH of the solution, and then you have to stir. So in our setup, we stir with the pH electrode, but you could also use a stir bar to stir the solution if you wanted to. And then this pH electrode is hooked up to the computer, which has the vernier software, and the vernier software collects the pH versus volume data. So you can see here, it just as time goes on, it collects the data and plots it out for you. So that would be what you would do if you were doing the experiment. So now there are two things that you have to do, there are two goals for this experiment that we have to get from the data, from the titration curve. The first is the concentration of the unknown acid, and the second is the value of Ka1 and Ka2. So let's take a look at determining the concentration of the unknown acid. So for those of you guys that have done experiment 16, all of you guys should have done experiment 16 by this point. We know that the way of getting the values for the equivalence point is to use the second derivative. So the second derivative shows us where the inflection point is. There's an inflection point right where the equivalence point should be. And when these traces cross zero, you get these nice sharp lines that go through zero. That intersection with zero tells you have the equivalence point. So we're going to use the data to determine the equivalence point. So if I jump over to Excel, and I have the data plotted here. If you look, the crossing point for this is at about, let's take a look. So it's at about like 3.75. So it's a little bit less than 4. So now there's a couple of ways that you can figure out the equivalence point using second derivative data. The way that I like to do it, because for this experiment we don't need to be, we need to be accurate, but we have to live within the means of our experiment. Personally, I think the simplest thing to do is to take the average of the 2 points around where the thing crosses zero. So you'll notice here at around 3.75, that's where we saw the thing cross zero on the graph. You'll notice that you have a very large positive number and a very large negative number. So as this thing crosses the zero, it's going to go from positive to negative. So that tells me, okay, my equivalence point is going to be somewhere between these two values. So what I do is, to get the number, I kind of estimate it by saying, let's get the average volume between those two. So let's say that the volume is going to be exactly in between those two numbers. So I type in average, I take the two numbers, the one on the positive side and the one on the negative side, I hit enter, and it gives me a value of 3.749. Then I'm going to bring that over and write that down on my data sheet. Now, in terms of sig figs, the best volume we can measure is out to two significant figures, right? So when you're measuring volume, I'm sorry, not to two significant figures, to two digits. So we can measure 3.7 something. So to estimate this data, I would estimate this as 3.75. And you'll notice that that's pretty much right in between. So in the accuracy of our experiment, using this average technique is a pretty good approximation, given that we can only go to 2 decimal points. Now, another way of doing it that Dr. Feruznia suggested to some of his sections was, you can fit this straight line to a line equation, and then using a bunch of data points, actually figure out where it crosses the zero. Either one is fine, but the average might be a little bit more straightforward to do while you're off at home without us to help you. So that's how I would do it. So this tells me that the first equivalence point in my data was 3.75. Now your data is going to be different, obviously, so you're going to have to do this for your data treatment. And then I can do the same thing and find the equivalence point for the second one, which should be at about twice the volume. So I can do the same thing for this. So now this is an interesting question. So if we look at the data for volume 1, I write that down. And actually, we can make a little correction here. So we said that it was going to be 3.75 with the correct number of significant figures. So with 3.75 mils of NaOH, we can do our calculation. So I take my volume, multiply it by the concentration of the base, 0.1012. I get the number of moles from that multiplication. And then to get the concentration of the acid, we take the number of moles and we divide it by the volume of the acid that we put in, which was 25 mils. And then I get a number here, which is 0.01518. And with proper significant figures, we would round that to 0.0152. So that kind of makes sense. This is a reasonable concentration for an acid. So now the question, though, is when you go in and you look at where V2 is at 7.5 mils. So you're probably wondering, how could we have two totally different concentrations? If you were to do this exact same process, you're going to get a concentration that's twice as much. And that doesn't make any sense. The concentration of the acid can only be one concentration. It can't be two concentrations. So we have to do a little bit of thinking here. What we're doing is, in the first equivalence point, we're titrating the first proton. So this volume is required to titrate the first proton. Then we kind of start over again, and from this point forward, we titrate the second proton. So what you need to do is we need to take away this beginning part, because to titrate the second proton, we start from here and go to here. So when you look at it, the volume required to titrate the second proton is V2 minus V1. And what you'll notice is that when you do the subtraction here, you get the same volume as we had above. Now, my data was simulated, so I used I wrote a quick script to simulate the data, and it's perfect because it's simulated. In the experimental case, you might get slight variations. You might get a slight variation from the first volume to the second volume when you do the subtraction. It'll be small, but it may be there. So what you're going to do is you're going to calculate the concentration from V1, calculate the concentration from V2 using this subtraction equation to get the volume, and then you're going to calculate the average from those two. And they should be close to each other, within 1 or 2 or even maybe 3%. It should not be something like double. If it's double, you probably didn't subtract out. You probably didn't do your subtraction to compensate for that. So you should make sure when you take your average that the two numbers are pretty similar. And then this is what we're going to report as the average concentration for the acid from the first and second equivalence points. We can't do anything with the third equivalence point because it gets washed out. So we just have to rely on the first and the second. Okay, so then the second question is how do we get the values for Ka and Ka1 and Ka2? And like in the first experiment, we're going to use Henderson Hasselbach. So if we want to get the Kas, we have to use our knowledge of Henderson-Hasselbach to know that when the concentration of the conjugate base and the concentration of the acid are the same, this log term goes to 0, and then we have pH is equal to pKa. So for the first deprotonation, at the half equivalence point of the first step, we have the case where we have the phosphoric acid and the H2PO4 minus conjugate base. So we have the triprotic and the diprotic condition. At that half equivalence point, these two things are going to be equal. So we can say at this volume of the half equivalence point, at half the volume of the first equivalence point, the pH that we get is going to be equal to the pKa1. And then we can also do the same thing for the second equivalence point. We can go in and realize that at half the volume of the second equivalence point, we are going to have H2PO4 minus is equal to HPO42 minus, so the diprotic and the monoprotic. So that term will go to 0 here. Now, if you look carefully, and you should pay very close attention, this is not half of the volume of the second equivalence point. This is halfway between the first and second equivalence point. So halfway between the first and second equivalence point is basically 3/4 of this second equivalence point volume. So you have to be a little careful when you do that. You're looking for halfway between the first and the second. Because remember, at the first we have all H2PO4 minus, and at the second we have all HPO42 minus. So halfway in between, we're going to have half and half of those things. So this is where you're going to get the second pKa from that pH. Okay, so this should give you enough information to do the experiment. Now, I've uploaded to Blackboard along with this video a modified data sheet. On this data sheet, you're going to enter your volume at the first equivalence point and volume at the first half equivalence point. Those are going to go in, and you're going to put your Ka1 and Ka1 data here, the pKa and the Ka1. The same thing for the second equivalence point. And then you'll notice in the concentration of the unknown polyprotic acid part, I've given you your volume and your concentration from the virtual students that did the experiment. So that's already here, and then you just have to calculate your equivalence points, the molarities, and then get the average. So if you have any questions, you can contact your instructor about this experiment. The data sheet will be due at the end of your lab session. So when your lab would normally end, that's when you have to upload the data sheet by. So good luck, and I hope that you guys are able to get some experience with polyprotic acids from this experiment.